Many of us remember from school that Pluto was once considered the ninth planet in the solar system. After 1992, its status was questioned following the discovery of several similarly sized objects in the outermost region of the system called the Kuiper Belt. A fierce debate arose among astronomers, and after the discovery of Eris, which is more massive than Pluto, the International Astronomical Union was forced to formally define the term planet in 2006, effectively excluding Pluto from the list of planets. Did we do the right thing or the wrong thing? We still can't say for sure. What we aim to explain in this video is how long it takes to get there, considering all the possible options. After 9.5 years of travel and 5 billion kilometers covered, going farther than any other spacecraft has ever gone, in 2015, New Horizons forced us to completely rethink our ideas about a celestial body considered at best a sterile ball of ice. Far from being a dwarf planet, Pluto has a diameter of 2,400 kilometers. It's a large, rocky core similar to Earth, wrapped in a mantle of frozen water, and perhaps even an underground ocean, itself covered by layers of more volatile ices like nitrogen, methane, and carbon dioxide. All these gases sublimate and then precipitate back onto the surface, freezing and creating an incredibly varied topography with exotic plains, craters, canyons, hills, steep mountains, and perhaps even ice volcanoes. And of course, all this differentiation makes Pluto one of the most colorful worlds in the solar system. So much so that New Horizons sensors revealed a landscape of stunning vistas. Scientists studying the images believe that the incredible variety of these landscapes comes from eons of interaction between the highly volatile and mobile ices of methane, nitrogen, and carbon monoxide, and the inert water ice, with fascinating cycles of evaporation and condensation. Cycles even richer than those on Earth, where there's only one material that condenses and evaporates: water. On Pluto, however, there are at least 3 elements interacting in ways we still don't fully understand across the entire surface. One of the most intriguing features of Pluto's landscape is surely the large heart-shaped plain known as Sputnik Planum. This enigmatic expanse is considered geologically young because it's crater-free, but its topography turned out to be much more complex than expected. The floor is made up of irregularly contoured nitrogen ice cells, where methane has filled the gaps. Hills of water ice float in a sea of frozen nitrogen. Ripple-like dunes and clustered pits make the smoother areas anything but monotonous. The plain seems to be dominated by active processes that slowly transform it, such as the thermal and cyclical convection of nitrogen ice. But that's not all. The atmosphere surrounding Pluto is equally spectacular. With its deep blue color, it contains a layer of haze and is colder and denser than expected. This affects how the upper atmosphere escapes into space and its interaction with the solar wind. We discovered that pre-New Horizons estimates of Pluto's atmospheric loss were greatly overestimated. We thought Pluto's atmosphere escaped like a comet's tail, but in reality it escapes at a rate much more similar to Earth's atmosphere. We also found that methane, rather than nitrogen, is the primary gas escaping from Pluto. This is quite surprising, as near the surface the atmosphere is over 99% nitrogen. Thanks to complex photochemistry, methane and organic compounds in the atmosphere are hit by ultraviolet rays from solar radiation, forming reddish soot particles known as tholins. These create low-altitude hazes and fall back onto the surface, giving it a brick red color. Besides being visually striking, these low hazes suggest that weather conditions change daily on Pluto, much like on Earth, and much more than on Mars, with the formation of very complex cloud systems. Another element that justifies our total disagreement with Pluto's exclusion from the list of planets is the presence of an incredible satellite system, consisting of Charon, 1,200 kilometers in diameter, plus 4 much smaller ones, with diameters ranging from about 40 kilometers for Nix and Hydra to about 10 kilometers for Styx and Kerberos. They have highly anomalous rotation rates, unusual orientations, and icy surfaces with albedos and colors very different from those of Pluto and its major moon Charon. There is evidence that some of them are the result of the merger of 2 smaller bodies, and the craters present date their formation to at least 4 billion years ago. reinforcing the idea that they formed following a collision that produced the binary system Pluto-Charon. Speaking of this rare double planet configuration, so similar to the Earth-Moon system, with the two objects locked in a gravitational resonance, always showing the same face to each other, what would you think of a planet that has a satellite in the sky almost 8 times the angular diameter of our moon as seen from Earth? Would you really call that a dwarf planet? In short, folks, in those few minutes the probes took to fly over it, Pluto revealed itself to be such a complex world that it immediately made us think we absolutely have to go back soon. But how? New Horizons took more than 9 years to get there. Is that a lot? Is that a little? To those unfamiliar with the distances and times that govern the cosmos, it may seem like an eternity. But can we do better or not? You can't answer this question without first understanding that the duration of a journey to such a distant celestial body depends on many variables dictated by initial choices, so there can't be a single answer. But how did the New Horizons probe reach Pluto so quickly? New Horizons was launched on January 19, 2006, when Pluto was still a planet. And thanks to its relatively small mass of about 1 ton, boosted by a powerful Atlas V launch vehicle, it is still the fastest spacecraft to have left Earth. When the rocket's engine in the launch vehicle's final stage shut down, New Horizons was traveling at 16.21 kilometers per second, 58,000 kilometers per hour or 36,000 miles per hour relative to Earth. Thanks to this impressive speed, it crossed the Moon's orbit just 9 hours after launch, while Apollo missions took 3 days to cover this distance. However, fast or not, the probe did not travel directly to its final destination, Pluto and its family of moons. Instead, New Horizons spent its first year in space taking a longer, indirect route through the solar system towards Jupiter. As it approached the giant planet, New Horizons began to accelerate as Jupiter's gravitational influence increased, while its trajectory began to change as Jupiter pulled the probe towards itself. Seen from above, the probe's path would have developed a sharp curve as Jupiter brought it into a new trajectory. On February 28, 2007, the small probe made its closest approach at about 2 million kilometers from Jupiter, then continued on its path, traveling about 4 kilometers per second, 14,400 kilometers per hour or 8,950 miles per hour, faster than before the encounter with Jupiter. This might be surprising. Where did this speed increase come from? Well, it was essentially stolen from Jupiter. The loss of speed for Jupiter is proportional to the size difference between the giant planet and the spacecraft. So, Jupiter was slowed by about 1/millionth of a trillionth of a millimeter per second. Thanks to this ingenious maneuver, 4 years were cut from New Horizons' travel time to Pluto in one fell swoop. There was a serious reason to make the journey as fast as possible. Scientists wanted New Horizons to reach Pluto before its thin atmosphere disappeared, freezing as the planet moved away from the Sun. Less happily, this great speed meant it was impossible for the probe to achieve orbit around Pluto. New Horizons flew past Pluto without stopping, effectively passing between the dwarf planet and its largest moon, Charon. No available propulsion system could have slowed the probe enough to enter orbit around Pluto. So, from this, it's clear that the duration of a journey to Pluto depends on several factors, including the very important one of a launch speed, then the type of propulsion used, the nature of the mission, flyby or orbital insertion, automated or crewed mission, and the position of Pluto along its highly eccentric orbit also play a role. Let's examine these factors one by one, okay? Pluto's distance from Earth varies. Pluto has a highly eccentric orbit, meaning its distance from Earth ranges from 4.28 billion kilometers or 28.58 AU at perihelion to 7.52 billion kilometers or 50.3 AU at aphelion. An impressive difference, isn't it? This means that to minimize travel time, missions should be scheduled when the distance is near its minimum. This is exactly what happened with New Horizons, which took advantage of the period when Pluto was near its perihelion. This is a significant limitation for current propulsion technologies, as the optimal launch window repeats at intervals of about 120 years. If New Horizons had launched when Pluto was at aphelion, it would have taken twice as long. Types of propulsion. Current chemical propulsion. Chemical propulsion is currently the most widely used technology for space travel. It uses the chemical reaction of fuels and oxidizers to generate thrust. As we've seen, using chemical propulsion and gravitational assists, the journey to Pluto can take between 9 and 20 years, depending on its orbital position. Chemical propulsion is well tested and reliable, but its efficiency is limited, requiring large amounts of fuel and offering relatively long travel times. Ionic and solar propulsion, near-future technologies. Ionic propulsion uses electricity to ionize and accelerate a propellant, usually noble gases like xenon, to very high speeds. Solar propulsion, on the other hand, uses the pressure of sunlight on thin sails. These technologies could reduce the travel time to about 7 to 9 years, depending on Pluto's distance from Earth at the time of launch. Ionic propulsion, for example, was successfully used in the Dawn mission to Vesta and Ceres. These systems are much more fuel efficient than chemical propulsion, but provide less thrust, making them ideal for long-duration, unmanned missions. Futuristic propulsion, nuclear and antimatter. Nuclear propulsion uses nuclear reactors to generate heat and thrust, while antimatter propulsion exploits the reaction between matter and antimatter, releasing enormous amounts of energy. With nuclear propulsion, the journey could be reduced to about 3 to 5 years, while antimatter propulsion could theoretically reduce travel times to a few months. These technologies offer enormous potential for reducing travel times, but are still in experimental development and pose significant technical and safety challenges. Types of missions. Automated flyby mission. An automated flyby mission involves a close pass of a probe without entering orbit around the planet. As demonstrated by the New Horizons mission, using a chemical propulsion and gravitational assists, a flyby mission to Pluto can take about 9 to 10 years. Flyby missions allow for close-up data collection without the probe having to slow down for orbital insertion, but the downside is that they offer only a brief observation period. The flyby of Pluto by New Horizons lasted only 3 minutes. Automated orbital mission. This mission involves the probe entering orbit around Pluto for extended studies. Using chemical propulsion, the duration could be similar to that of a flyby. It offers a prolonged period of observation and data collection, but requires more fuel and more complex maneuvers for orbital insertion, as well as significant deceleration in the final stretch. The estimated travel time would be 12 to 15 years. Crewed mission. A crewed mission to Pluto would represent one of the greatest challenges in space exploration. With current technology, a crewed mission, including orbital insertion, would take about 15 to 20 years. The spacecraft would have to be a large vessel where astronauts could live for years, making it extremely heavy and requiring an enormous amount of fuel. There is no possibility of this happening without a propulsion system capable of reducing the travel time to just a few months. To conclude, planet or dwarf planet? Pluto doesn't care. However we decide to classify it, it will continue to travel silently along the edge of the solar system. If we want to try sending another spacecraft to its vicinity, perhaps equipped with a rover to explore its surface, we will need to find a more powerful energy source as soon as possible. And above all, we should keep in mind that the longer we wait, the farther Pluto moves away, greatly increasing travel times. All in all, the simplest solution would be to send another New Horizons right away, this time to enter orbit. If launched in about 10 years, it would arrive around 2045, when Pluto would still be relatively close at 39.5 AU or 5.9 billion kilometers. Why is it so tough to go to Alpha Centauri? How long would it take us to go there? Before diving into that, let's recap the situation a bit. Alpha Centauri is a system made up of 3 stars: Alpha Centauri A, officially Rigil Kentaurus; Alpha Centauri B, officially Toliman; and Alpha Centauri C, officially Proxima Centauri. Alpha Centauri A and B form a binary pair of Sun-like stars orbiting their common center of gravity, while Proxima Centauri is a red dwarf orbiting the main pair at a distance of about 0.2 light-years. Then there's Proxima B, a planet orbiting Proxima at about 0.049 astronomical units, over 20 times closer than Earth is to the Sun. but still within the star's habitable zone. Proxima is only 4.246 light-years from Earth, roughly 40 trillion kilometers, making it the closest star to our solar system. This also makes Proxima B the closest known exoplanet to Earth and the 8th on the list for Earth Similarity Index among all cataloged exoplanets. So it's no surprise that since its discovery in 2016, Proxima B has become the largest for a potential interstellar mission. This marked a significant leap into our determination to achieve this feat. Before its discovery, our desire to reach Alpha Centauri was rather vague and ambitious, but with the discovery of a potentially habitable planet, we finally had a clear goal. Isn't it true that Proxima B could become our second Earth in the distant future? Okay, folks, let's not kid ourselves. The distance to Proxima Centauri, our nearest star, is 266,000 times greater than the distance to the Sun, and 103 million times greater than the distance we had to cover to reach the Moon. Impressive, right? Even a beam of light traveling at the maximum speed allowed by the laws of physics takes 4.3 years to reach us from Proxima, while it takes less than 8.5 minutes to bridge the gap between us and the Sun. These numbers, in their relentless inevitability, encapsulate the problem of interstellar travel, a daunting abyss of time and space. End of the line then? Unlucky to have drawn such a high hurdle? Well, maybe not actually. The data indicates that the typical distance between stars within 30 light-years of the Sun is about 9 light-years, more than twice the distance to Proxima. Statistically, much closer than expected then. In light of these facts, we might need to revise our initial impression and conclude that we've been quite lucky to have such a similar star system so close by. Sure, it could have been better, but it wouldn't have been logical to expect a star right in our backyard, with all the possible gravitational consequences, some of which could be quite negative. This allows us to look at the endeavor with a bit of confidence and optimism. Optimism that, however, plummets when we consider our current ability to mount a mission capable of us getting there. To realize our current technological shortcomings, we just need to reflect on the fact that Voyager 1, currently the fastest human-made interstellar object, is moving away from the Sun at 61,000 kilometers per hour or 38,000 miles per hour, a speed that, if maintained, would allow it to reach a star at Proxima's distance in no less than 75,000 years. While if we relied on the fastest probe ever launched, the Parker Solar Probe, capable of reaching 700,000 kilometers per hour or 435,000 miles per hour, we could make it in just over 6,500 years. A bit too long to ignite our dreams. It's clear then that traditional chemical fuel engines, even with the gravity assist from Jupiter and Saturn, are entirely inadequate for such distances, and a drastic technological leap is necessary. In this regard, many ideas have been proposed, from rockets that use nuclear fission and fusion to those powered by matter-antimatter annihilation to enormous light sails. These are only theoretical solutions, which would still require decades of development and enormous technological and economic efforts to materialize. For a distant future, and still to be verified, some have proposed the use of warp drives, which exist only in our imagination, or wormholes, so far only imagined. Fanciful solutions based on extreme hypotheses of general relativity, which some say could allow travel at speeds greater than light. But unfortunately, it's not just about building bigger, better, and faster spaceships. It's not just about waiting for science and technology to take their course. As we will see shortly, there is a physical impossibility that slows down, if not prevents, our plans for free and fast navigation in the galaxy. For interstellar travel to become appealing to humans, triggering that cocktail of aspiration, ambition, curiosity, and competition that motivates our greatest endeavors, we would need to significantly increase speed. But this is absolutely impossible for several reasons, and this impossibility is also demonstrated by the implicit conclusions of the famous Fermi paradox. As Albert Einstein first noted in 1905 in his special theory of relativity, no object with mass can exceed the speed of light. Einstein established this limit based on considerations that seemed, and still seem, to clash with the common sense, with which we are used to evaluating the physical phenomena of our daily lives. But this does not change the fact that the limit has been verified in many experiments, and as far as matter and the universe we know are concerned, there is no longer any reason to doubt its existence. Energy and mass are equivalent entities that can transform into each other. This is exactly what happens when we accelerate an object, even if we don't notice it. The energy we impart to it slightly increases its mass. As the speed increases, however, more and more energy is required to further increase the speed, because more energy is converted into mass. This mass increases the system's inertia, opposing further increases in speed. In practice, the closer you get to the speed of light, the more massive and immovable the object becomes. Objects with mass, in short, resist being accelerated to speeds close to that of light, and the closer you get to that speed, the harder it becomes to accelerate them further. And even if some magical device could instantly reach the speed of light, it would still take 4.3 years to get to Proxima Centauri. This means that even traveling at the maximum speed achievable in our universe, our species could, at most, explore the vicinity of the Sun, but certainly could not establish a network of trade routes across the entire galaxy. But let's not give up so quickly. Maybe we're missing something. Yes, because mass is not the only quantity that varies with speed. Another factor to consider in relativistic space travel is time dilation. Contrary to what classical physics postulates, time does not flow uniformly for all observers, but rather more slowly the closer the observer measuring a given event gets to the speed of light. Leaving aside the physical and mathematical explanation, we must trust the fact, absolutely verified, that on board a spaceship leaving Earth and accelerating to relativistic speeds, time passes more slowly compared to the planet it just left. Imagine a spaceship traveling at 95% of the speed of light to a planet 9.5 light-years away. A stationary observer on Earth would measure the journey time as distance divided by speed, or 9.5 divided by 0.95 equals 10 years. The spaceship crew members, on the other hand, experience time dilation and thus perceive the trip as taking only 3.12 years. In other words, between leaving the Earth and reaching their destination, the crew members age a little over 3 years, while 10 years have passed for people back on Earth. So does time dilation solve the problem? Well, unfortunately, no. As we saw earlier, to accelerate a mass more and more until it approaches the speed of light, it would ultimately require practically infinite energy. No known form of propulsion could give us this gift. And even if the energy problem were somehow solved with methods we cannot currently foresee, there's also the fact that a spaceship traveling at a speed very close to that of light would be in a particularly dangerous position. Space is not empty. It's actually full of wandering atoms, which sometimes gather into more complex forms like gas and dust clouds, galaxies, stars, and planets, while other times they remain solitary atoms traveling towards nothingness and probably won't collide with another atom for thousands of years. Well, one thing is the probability of a collision between two hydrogen atoms in a cubic centimeter of space. Another matter is the certainty of the enormous flow of particles that will collide with the spaceship during its journey. Particles that are almost harmless at low speeds, but with acceleration, they turn into a deadly rain of projectiles and highly penetrating ionizing radiation, capable of severely damaging the hull and making it dangerously radioactive for the occupants. These particles, intercepted at speeds close to that of light, would acquire such great energy as to become lethal for any form of life on board. Not to mention that at such speeds, even passing through a thin nebular veil could completely destroy the spaceship. Some scientists believe that interstellar matter alone will be enough to prevent a spaceship from reaching speeds greater than 1/10 of the speed of light, which, as we've seen, is absolutely insufficient to support a network of large-scale commercial and exploration routes. Even if all these difficulties were overcome, there would still be another insurmountable problem. Time dilation would cut all ties between the traveling spaceship and its home planet. Only the crew would benefit from this time shortening, while for the inhabitants of Earth, time would continue to flow at its usual pace. So for the 11 years perceived by the crew would be 2.5 million years for them. The astronauts would leave knowing they would never see their families, relatives, or friends again, unless they brought them along or didn't have them at all. Upon their return, they would find a society profoundly different from the one they left. Moreover, such a method of travel could not allow for the existence of interstellar institutions, like the United Federation of Planets suggested in Star Trek, based on commercial and cultural exchanges between different races, which presuppose a homogeneous level of technological and social progress. Homogeneity that is not compatible with the times required for interstellar travel is conceived. What could motivate a future commercial enterprise to send its goods to the other end of the galaxy, knowing it would never see or communicate with the spaceship carrying its cargo again? Any spaceship venturing into the realm of Einsteinian relativity would become, in practice, a world unto itself, without a homeland and without a past. So what would be the point? Indeed, this is a scenario destined never to materialize. Enrico Fermi tells us this with the logic of his famous paradox. The Italian physicist asked, if our galaxy really hosts technologically advanced civilizations, why aren't their representatives already here? A question that can be answered with a simple consideration. The universe, as we know it, has existed for about 13 billion years. And based on what has happened to our species, it takes 5 billion years for a planet of a solar-type star to generate intelligent life. This means that millions of civilizations evolved before ours and had eons to develop technology capable of space travel. Their absence is therefore proof that traveling from one star to another at the speed of light is an endeavor beyond the capabilities of any civilization. And thus, the answer to Fermi's question is this: if they're not here, it does not mean that extraterrestrials do not exist, but simply that physics does not provide solutions capable of nullifying distances. Neither warp drives nor space-time tunnels. Nothing at all. We, like all other inhabitants of the galaxy, are destined to remain confined to our little backyard, content with a few laborious exploratory trips to the 2 or 3 nearest stars. This is all in terms of exploration conducted with human crews. The situation would be different if interstellar exploration meant launching small automated probes instead. Initially, missions directed at the stars will likely be conducted with intelligent robotic probes, miniaturized beyond any currently conceivable limits, capable of traveling at 0.1 C. But just extrapolating a bit from the extraordinary progress in biotechnology, genetic and molecular engineering, embryonic development in cellular physiology, it becomes clear that even with simple probes like these, humans themselves could quickly spread throughout the galaxy, as proposed by physicist Frank J. Tipler and described by Arthur C. Clarke in the fascinating novel The Songs of Distant Earth. In practice, this would involve creating so-called von Neumann probes, intelligent and automated, that upon reaching their destination would be able to build copies of themselves and habitats for any living beings, including humans, from available raw materials, synthesized on site from genetic code information and instructions for embryo generation and development. Once the colonization of a world is successfully initiated, the von Neumann probes could then build new interstellar spacecraft and new automation destined to fly to other star systems to repeat the process. The propulsion? Sails. A promising proposal is represented by star-wisp laser sails, where the problems of mass and heat are solved by eliminating the engine, replaced by the pressure exerted by a beam of radiation directed at an ultra-light sail. However, the problems of energy and travel duration must be addressed with highly innovative solutions. Since the original idea was formulated in the early 1980s, the concept of the interstellar sail has undergone several revisions and improvements, mainly to limit the energy requirements of the journey and make its operation more plausible. In any case, the main elements of the system would consist of a powerful laser or microwave transmitter, probably placed in space, a gigantic lens used to focus the radiation into an extremely culminated beam even at great distances, and the actual interstellar sail capable of intercepting the radiation and being significantly accelerated by the pressure thus exerted. And when we say sail, we don't mean a racing spinnaker, but something at least 6 kilometers in diameter and weighing only 30 grams. Accelerated to just 0.2 C in just 2 weeks, the star wisp could reach the Alpha Centauri system in just 21 years. So we leave you with this faint hope. Perhaps the youngest among you will witness the launch of the first probes. It won't be like seeing the Enterprise take off, but it will still be a great thrill. Make good use of it.